Welcome back. In this session we are going to see how to write unrestricted grammars. As a reminder, unrestricted grammars are equivalent to type 0 generative grammars in Chomsky-Schutzenberger's hierarchy. Unrestricted grammars can be more powerful than regular grammars, than context-free grammars, and even than context-sensitive grammars. They can recognize any recursively enumerated language, therefore any natural language, and can be processed by Turing machines. A famous formalism used to write grammars that are equivalent to unrestricted grammars are HPHG, which has been used in Stanford University. So in Nudge, unrestricted grammars are similar to context-sensitive grammars, but they can also contain variables and constraints that can be written in the output. And therefore, they can be used to replace matching text, recognized by the input, with the corresponding grammar output. The grammar output can be anything, for example, transformation of a text, paraphrases, semantic representation, etc. But if associated with multilingual resources, such as multilingual dictionaries, the output can be in another language, so you can produce translation. So a very simple example. So as unrestricted grammars can contain variables in the output, so for example, you could have a grammar that recognizes Joe arrived, period, Eva left, and Joe arrived is going to be stored in a grammar variable S1, Eva left in variable S2, and then as an output you could produce S1 and S2. So if you have the text Joe arrived, Eva left, you could write a very simple unrestricted grammar that will produce Joe arrived and Eva left. You can also use morphological operators to modify the content of a variable. So for example, if you have a sentence, he eats, you can store eats as in a variable, let's say call it V, and then you can produce the text, they want to, and then you copy the variable V, but this time you lematize it with this underscore operator. So in the result, so if you have the sentence he eats, this grammar will produce they want to eat. There are of course more sophisticated uses of morphological operators. So for example, in this grammar you have N0, V, N1, so you have a noun phrase followed by a verb in the third person singular, followed by a noun phrase, and you can produce N1, so this would be this one here, is, and then you take the verb here and you put it in past participle, and then you copy by, and then you copy the variable N0. So if you have Joe sees Mary, Joe will be stored as N0, sees as a verb, and Mary as N1, and then this grammar will produce N1, so Mary is, and then this one here will produce from sees, it will produce seen, because this is a past participle of the verb, by, and then N0 will be a Joe. So Joe sees Mary will be transformed, will be rewritten as Mary is seen by Joe. So in order for this to work, of course, you need to have the verb see represented as a lexical entry, and its inflected paradigm here must be able to produce this PP code, which is here associated with the form seen. So if $V is equals to sees, then $V underscore, I remind you, is the lemmatized form, the lexical entry, so it will be C, and then $V underscore V will match, will represent all the verbal forms associated with C, so see, sees, saw, seen, and seeing, and then $V underscore V plus PP will only match seen, which is the only form, the only verbal form associated with the code PP. There are many applications of these transformations. One is this one here. So Esperto is a system for paraphrasing Portuguese text built by Barreiro and Mota from INESC ID. So from lexical resources such as a lexicon grammar table here, and that was put in Nuge as a Nuge dictionary here, and a grammar, or an unrestricted grammar. They were able to write a system, Esperto, that can take complex sentences in Portuguese and then paraphrase them with many properties. So, for example, using a human intransitive adjective, a predicate noun with a support verb phaser, etc. So let's say we want to write a transformational grammar for French or English or any language. How many transformations we would have to write? So let's see. So we could write a little grammar, an unrestricted grammar, that takes the sentence John ate an apple and pronominalize its subjects. So he ate an apple. So we could call this graph, this grammar, pron 0. So we would have also pron 1, pron 2. We would have a grammar such as passive. John ate an apple was eaten by John. Negation, John ate an apple, John did not eat an apple. Cleft, question, etc. But the problem is the grammar that can be used to take an active sentence and put it in passive is different from the grammar that will take the passive, that will recognize the passive sentence and produce its active. So each transformation will need two graphs and not only one. So if we have, let's say, 1,000 transformations in English, now we need 2,000 graphs to write. Actually, it's going to be much more complicated than that, because for one transformation, we cannot have only one grammar to write the passive, not even two to write the passive and then to the reverse transformation. But each sentence that can be transformed, for each transformed sentence, they can also accept the passive. So we have to take care, we have to take into account sentences that have already been transformed. So for example, if we have the sentence, John ate an apple, that was pronominalized, it's subject pronominalized, so we get he ate an apple, we cannot use the same transformation as before, because it would produce an apple was eaten by he, which is not correct. So we need to write a new grammar, a new graph, to take care of this sentence, for example, to produce an apple was eaten by him. If we have a sentence such as John gave an apple to Mary, and then we pronominalized the second complement, so John gave her an apple, we cannot use either passive or passive one. We have to create a new graph, a new grammar, to transform it into she was given an apple by John. And sometimes we cannot even put in a passive transformed sentence. For example, of course, if we already have John ate an apple, we have already applied the passivation, so we have an apple was eaten by John. It doesn't make any sense to apply passive to this sentence. Negation, if we have John ate an apple that gave John did not eat an apple, we need to create a new passivation graph, grammar, let's say passive 4, that will produce an apple was not eaten by John. And notice that it's different because there was the verb auxiliary verb did is no longer there. Passive 5, 6, 7, 8, 9, 10, we have already 11 passivation operations that we need to take into account if we want to put in the passive these 11 transformed sentences. So from a theoretical point of view, if we have 1,000 elementary sentences in English, then how many graphs we would have to write in order to take into account combinations of two transformations? Well, basically it's 1,000 per 1,000. And if we want to combine 3 combinations, that would be 1,000 to the power of 3. And if we want to take into account sentences that have 7 combinations of transformations, that would be 1000 to the power of 7. And notice that a sentence such as, "It is not like Joe wanted to stop being her lover," is not unnatural. I'm sure we can find these type of sentences in regular texts. And how many transformations are there here? Well, 1, 2, 3, 4, 5, 6, 7. So it's totally natural to have a sentence that has been transformed by using 7 transformations, but it's totally impossible to think about writing 1000 to the power of 7 grammars. So we need another solution. So remember that all the linguistic resources that you build with Nuge has to be neutral, which means they can be used both to parse text or to generate text. For example, a morphological grammar, such as this one here, France, can be used both to recognize word forms in a text, France, francophone, francophonie, français, Frenchman, redéfrancisé, redefranchify, francisation, frenchifization, etc. So this already recognizes 40 words plus their inflected forms. This graph can be applied to recognize word forms, so in parse mode, but you can also use it to produce a dictionary. For example, here, by clicking Grammar Generate Language on this graph, we will produce a corresponding dictionary, francisé, the verb, paradigm aider, etc. So we are going to use the same trick, the same functionality, which is all linguistic resources are neutral, not only to use syntactic grammars to parse text, but also to produce text. So if we have a very simple syntactic grammar, such as this one, NP, VNP, so you have a subject, a verb, and a complement. This grammar will recognize this simple elementary sentence, but also transform sentences, such as object, VPP, so past participle, by subject. It is not subject who, verb, NP. So this grammar, for example, would recognize Joe loves Leah, but also it is not Joe who loves Leah. Leah is loved by Joe. And notice that these variables here, this variable subject is refers to the exact same variable as this one and as this one. So this is only one variable with only one value. So if we use a generate function of Nuge to generate all the path, to explore all the paths of this grammar, we will get something like that, you see. Object is VPP by subject, determiner noun, verb, determiner noun, etc. And you see there are these variables there. So now it's just a matter of giving a value to these variables, and we can do that during parse mode. So if we give the value, let's say Joe, to the subject variable, it will not only be set here, but also here and there and everywhere in the grammar. So during the parsing step, we will set values to variables. So let's say we parse the text Joe loves Mary. The variable subject will be set to John. Loves will be the value of the verb, and Mary will be the value of object. And then when we use the grammar in generation mode, so when we explore the graph and produce all the sequences that are recognized, that are represented by the grammar, now Nuge knows what are the values of these variables, so it can replace the variables with their value. And that's how we get, if we parse the text John loves Mary, the former text here where there were variables, now these variables can be set to their proper value. So now we have, it is John who does not love Mary, John does love Mary, John does not love Mary, has loved Mary, etc. So there are. It's not enough that we want to produce all the sentences that are transformed. We want also to name the transformation. So, for example, when we produce a passive variant of the sentence, for example, here, Leah might have been loved by him. We want to produce a feature, let's say, plus passive. Here we want to. If we go here, we want to describe the sentence as being nominalized, and here there is a cleft, etc. So if we add these features to the sentences, now we not only can produce all the sentences that are transformed from the initial sentence, but we can also describe their properties, what transformations were applied to them. We have the same thing, of course, in many languages in the Nuge community. So this is an example for Italian. Maria osserva il ragazzo, and then this very simple sentence produces over 1,600 transformed sentences. Each of them have been described, and this is in French. Luc aime Léa, same thing. And now one interesting thing is, let's say we have a bilingual dictionary, so we can use the bilingual information, let's say the translation from French to English, in order to produce the translation. So this is a very simple example. Let's say we have the French text, le petit crayon rouge. Le, here, means the. Petit means little, it's an adjective. Crayon means pencil, it's a noun. And then rouge is an adjective, it means red. So this le petit crayon rouge will be recognized by this grammar. So now let's say we have in a dictionary petit described as an adjective with its translation here in English. En equals little. And the same with crayon. In the dictionary we have crayon as an entry, and then here en equals pencil, and then rouge has been translated in English as red. So now when we apply this grammar to le petit crayon rouge, we are going to produce, you see, le will produce the, and then petit will produce $A, $en. So what does it mean here? It's the variable $A, which its value is petit, right? Le petit crayon rouge, petit is a value of variable A. So if A as a value, the atomic linguistic unit petit, then $A, $en is the value of property En of the lexeme here, and property En as little as value, so $A, $En is little. And the same with pencil here, pencil, crayon as a property En. So if N is crayon, then $N, $En is pencil. And if you want to put it in the plural, you're going to get pencils. So if we have le petit crayon rouge, this grammar will produce the little red pen. Notice that petit is before the noun, and it's automatically translated right away. The noun is not translated right away. We wait to translate all the adjectives, because in English adjectives are always before the noun. So le petit crayon rouge will produce the, little, like nothing here, red, and now there are some constraints, just like in context-sensitive grammars. If crayon is singular here, we go here and we will produce the English translation in singular, the little red pen. So we will produce the word pen here at the end. If we had les petits crayons rouges, crayon in the plural, so we would go here, noun plural, so we would produce pencils. So here is an example. Nos petites tables will produce our little tables. Le joli crayon rouge, the pretty red pencil. Leur joli crayon rouge, their pretty red pencils. So in the Nuge community, there is probably a dozen of machine translation systems that have been built. Arabic French machine translation, Belarusian Spanish, Greek Spanish, English Italian, Portuguese English, etc. This is a translation of relative clauses in Arabic that has been translated into English. And as a reminder, in the introductory presentation, I showed that Google Translate basically couldn't translate these sentences correctly. There are many applications of unrestricted grammars. It's easy to write little simple grammars, such as to transcribe phonemic into orthographic notations, or Hela Ferry from the University of Sfax wrote a system that can translate French to Arabic and Arabic to French transcriptions of proper names. So, for example, a name such as Mohammed can have 4 or 5 transcriptions with Latin letters. There have been some applications to rewrite a scientific medical text with simpler paraphrases. Parse a text and produce its abstract. Actually, one could consider sentences such as somebody built the Eiffel Tower could be linked by transformation to their corresponding questions. So we could link a question such as who built the Eiffel Tower to its potential answers. X built the Eiffel Tower. The Eiffel Tower was built by X. X has been instrumental in building the Eiffel Tower, etc. And then with a simple Google search, we could look for these patterns in a text to get the answer. So this would be a question answering system. There have been other applications such as semantic analysis of a text. For example, you can parse a text and you produce its semantic representation either in predicate form, such as, for example, Joe gave an apple to Eva, would be represented as predicate give with the 3 arguments, Joe, apple, Eva. And recently in the web semantics, a semantic representation that is widely used is RDF in XML format. And there are some applications of Nuge that can translate an English text into RDF representation. So if you are interested in Nuge applications, you can go to the Nuge website. In the references page, you're going to see 500 references to applications. As of now, we have covered over 30 languages. So all these tutorial sessions that I presented could have been made in other languages. So at this point, and after these 16 presentations, I need to congratulate you. You now know how to use unrestricted grammars to perform transformations, compute paraphrases, and produce semantic analysis, compute translations, etc. So thank you very much for having followed this